Hello everyone, my name is Mark. Welcome to my multivariable calculus Calc 3 videos. And today we're going to talk about cylinders and quadric surfaces. And as usual, we can start with some quick questions. So first one is, right, this first one we're going to talk about some basic definitions about conic equations. So I presented you 4 different types of conic equations, and I would like you to first of all identify what these shapes are, and I would like you to start to recall the equations that describe these conic equations. Okay, so so on the top left we have the circle. I think everybody's familiar to that, and then the x, everybody knows about x squared plus y squared equals to r squared, but the h and the k describes the displacement of the circle. Let's say we have some numbers over here, and the y and the k will be the vertical and the horizontal and vertical coordinates of the center of the circle. And then we have the hyperbola, right? Everybody knows y equals to x squared plus k, right? The a coefficient tells you how steep the curve is, and then the h is the horizontal shift, and then the k is the vertical shift as well. And this is a is greater than 0, and this is a is less than 0. And then we have the ellipse, right? Ellipse is sort of the special case of a circle. Circle is a special case of ellipse. And then we have a squared plus b squared. That tells you that is the semi-major axes and the major axes of the ellipse, and then the rightmost value should always be 1. And the hyperbola, it's a similar looking equation that compared to the ellipse, and the way you can tell these equations apart is that both of them are to the square for the x and y components, right? X squared, y squared, x squared, y squared. But the only difference, or the major significant difference is that these two square terms, they have the same coefficients for the ellipses, but they have the opposite signs for the hyperbola. So that's how you can tell the ellipse and hyperbola apart when you identify them, when we will use them later. And then for parabola, it's pretty simple because the y is on the first power and the x is on the second power, or vice versa. Okay, now let's level up a little bit. And these are the new things that you have learned from this lecture, right? These are quadric surfaces. So before we dive into how to identify them by looking at equations, I want you to think about, I want you to start with, how can you recall them by their shapes, right? Let's think about that for a moment. Pause the video if you need to, right? Don't always rush to the solution. I want you to think about these questions critically. All right, so the first one, we have the ellipsoid, right? So first one, we have the ellipsoid. That's just you have the special case as a sphere. And then if we go down, right, this is the elliptic paraboloid, right? So we have the ellipse right here, and then we have a parabola right here. And then as we go down, we have the hyperbolic paraboloid. So we have the hyperbola going right here, right? And then we have the parabola going this way, and we also have the parabola going this way. So it's two parabola, one hyperbola. So hyperbolic, parabolic. And then we have the cones, right? So cones are circular cones, elliptic cones. They're all the same. The idea is that we have some circles and ellipse, and then these are straight lines connecting them, okay? Straight lines. And we have the hyperbola of one sheet, right? The hyper is coming from the hyperbola, right? I hope everybody is understanding that at this point. So you have the hyperbola one way, and you have the vertical them this way, right? And then you have the circle or ellipse, depending on the configuration. And it's one sheet. It's continuous, right? It's crossing through the origin, or crossing through the zeros, the xy plane, yz planes. And then you have the hyperbola of two sheets, right? The difference is that compared to the one sheet is just that these two surfaces are not connected with each other. So I know some students would like to memorize these. Oh, this is the something to the square, something to the one to the first power, something to the second power, and these are the plus sign and minus signs. They like to memorize identifying the shapes by looking at the equations themselves. For me, I have helped many students over the years with Calc 3, and my suggestion towards surface identification is never to memorize these things in and out. You can. I think it's a good practice for you to, let's say, hey, I know what this basic equation of an ellipsoid looks like or sphere looks like, right? That's easy enough for you to memorize, and that's no problem. I have no problem with memorizing that, and I can probably go ahead and memorize elliptic paraboloid because I think it's fairly easy to identify, as long as you can see it through. But the rest of them, I would not recommend you to sort of just brute force it through identifying these equations. So I will show you an easy and reliable way to identify them later on, okay? But right now I want you to just memorize these name of the surfaces by looking at their shapes. All right, so this is what we're talking about, right? What is an effective way to visualize surfaces in 3D? So in this case, I'm assuming that you are given an equation, but you are not given the graphics of that equation is describing. So the effective way, it may not be the fastest way, but I guarantee you this is an effective and highly reliable way to visualize these surfaces. What I'm talking about is something called traces. I'm sure the professors have taught you how to draw the traces, and later on I will show you how to effectively utilizing traces to visualize 3D surfaces. Okay, but right now I'm telling you that traces is the effective way to visualize them. All right, second question. What should you do when the trace just simply doesn't exist, right? So let's just say the trace, you try to find the traces and you set z equals to 0 when you do the xy trace. It doesn't exist, right? The equation simply doesn't exist. What do? Well, we set z equal to 0, right? Is there any chance that we can set them, to a different values, right? Let's say we can set it to z equals to k. We can represent this. We can let z be any values instead of strictly at 0. In that case, we can just treat z as a constant number, and then we have left with two variables, and then we can identify the conic equations of that trace. Okay. What's the difference between traces and level curves? And I think this is, at least I have learned this early on, and I found this really helpful through my studies of Calc 3. But I think some of the professors don't really mention that early in their courses, which kind of confuses me. But I'm gonna hear the mention anyway. The traces is strictly you set x equal to 0, right, or y equals to 0, or z equal to 0, to find different traces that you want. Level curve is a little bit different. It only focuses on the xy plane. So, but instead of setting z equals to 0, you set that equal to k, right? As we discussed before, right? You can not only set z equals to a variable to 0. You can also set them to a specific constant. So in this case, level curve is sort of a collection of those graphs when you set z equals to different values. It's kind of like we're stacking different curves together, and I will show you an example of what that means. So, right, so these are isobars. I'm sure you have seen these graphs along the way, in your daily life. In this case, these isobars are pressure contours, right? Pressure, these lines are lines of equal pressure, right? This is 1030, 1030 of whatever the or whatever the unit of that pressure is, and we can replace this with temperature, right? I think that's no problem, and then we can even so the pressure and temperature is probably the most two common example in our lives, and then we can use an example. Let's say z equals to 1030 right here, right? Z equals to 1030 right here, z equals to 1020 right there. So that is the idea of the, and this is an example of level of contour plots. Okay. So, and then today let's go ahead and start with solving these type of problems. So, I'm gonna go ahead and pull up some. One second. Okay, so I'm gonna switch some orientations. So let's go ahead and solve a problem, and then demonstrate you what I mean by using traces to solve the problems. Let me go ahead and rearrange my notes really quickly. So this is the same question, and then the question asks you to identify the surface, which is this, through completing the square, right? So let's zoom out a little bit, right? So this is obviously what I call a surface identification problems. Why? Because you have the keyword identify the surface right here, right? And if you look at your answer choices, you will see a bunch of names of quadric surfaces. Okay, so that's how you can identify you are dealing with a surface identification problem. So to solve this type of problems, there are a few simple steps that you need to follow. First of all is identify the standard form, or STD, of the surface equation, right? So this is the reason why I'm proposing so much about using traces, because if the surface equation is not arranged in the standard form, which is all of the variable terms should be grouped together, and that's what they call the standard form. If the equation is not in the standard form, you cannot use the memorization techniques that you have developed to identify this equation, these surfaces. They just simply won't work. They only work when these equations are in the standard form. So you have to identify. So let's go ahead and obtain these the standard form, right? Let's go and I said complete the square if you need. So the first step for our case is to complete this, to rearrange this equation, right? So let's rearrange them. So 2x squared minus 4x plus minus 2y squared plus 3z squared equals to 0. All right, it's the same equation. I just rearranged them. And for my convenience, I'm going to divide everything by 2. So x squared minus 2x minus y squared plus 3 over 2z squared equals to 0. Okay, so to complete the square, right, I think everybody agrees that the only term that we need to deal with here is the x squared. You might need to deal with more than one, but x is the only one we have to worry about in this problem. So to complete the square, we're gonna add everything, add the left side and right side of the equation by 1. So x squared minus 2x plus 1 minus y squared plus 3 over 2z squared equals to 1. And then we can complete the square right here. X minus 1 squared minus y squared plus 3 over 2z squared equals to 1. And here we have the standard form. Okay, so that's step number one, right? Step number one. And then step number two, right, is to obtain the 2D traces by setting one of the variables to 0, right? And I want you to draw them out, right? If you have the time, if you have the ability to do so. So, right, and then if one of the equation of the trace does not exist, right, as we have discussed before, we can go ahead and set this variable to k and to sort of try to continue to identify the shape of the 2D traces. Okay, so step number two we're going to do is, let's just say we can start with finding the xy trace, right? Xy, right? So z equals to 0, right? The missing variable, right? Z is missing, so we set z equals to 0. What we will get from this equation, right? From this equation is x minus 1 squared minus y squared plus 3 over 2 z squared equals to 1, right? By looking at the conic equation right here, never mind. Sorry, my bad. I should have not written that down. But what we can see here is that we have an x squared term, right? It's a square term, and we also have a y squared term. So both the variables are squared, but look at the signs of the x square and x term and y term, right? So they are opposite signs, right? And this tells us this is a hyperbola that we're looking at, right? Both terms are squared, and the signs of two terms are opposite. So this is a hyperbola. All right, let's continue this, and let's do this time. Let's be a bit faster. All right, so we have xz trace, right? So we are going to have x minus 1 squared minus plus 3 over 2 z squared equals to 1. So this is going to be a circle. I think everybody agree with me. Or circle, or never mind, it's a ellipse. Right? And then yz trace. All right, we're going to have negative y squared plus 3 over 2 z squared equals to 1. This will give us another hyperbola, right? Both variables are power to the square, right? Power to the 2, and then the signs of the variables are different. So again, it's a hyperbola. So that's step 2. So we need to figure out the shape of the 2D traces. So, and then step 3 is each trace. The reason why we are finding the shapes of the traces is because each trace is a side profile of the surface. Okay, so match the surface to the, and then we will match the surfaces to the match the traces to the corresponding surface. Right. So what I mean is actually the combination of traces. Right. Match the the combo of traces to the corresponding quadric surfaces. Okay, so by the way, just to elaborate a little bit more, right? XY trace, you're looking at this quadric surfaces along the z axis, so sort of your eye is aligned with the z axis, and then the xz trace, right? You're viewing the surface along the y-axis, and then the yz trace, you're viewing the surface along the x-axis. So for 3, right, is we have referring back to our to this to these graphical definition again. I think, and that is why I think you need to memorize these shapes graphically rather than numerically. So for this particular problem is that each trace, sorry, never mind. Right, we have two sides, right, two side picture of this surface is hyperbola. Right, so we can go ahead and immediately eliminate these two, right? Because they have no hyperbolas involved, and then we can eliminate the cone as well. And then one is circle, right? So because we have hyperbola, we have circle, we can quickly eliminate these four quadric surfaces out. But so that tells us this is a hyperboloid, right? So this is a hyperboloid. But the question is, one sheet or two, right? So since, right, I hope I don't know if you noticed about the hyperboloid of one sheet and two sheets. The one thing that's different about the one sheet is that the traces, the 2D traces exist at the XY plane, YZ plane, and XZ plane, right? So since traces exist at XZ, XY, YZ, XZ plane, right? These are Z equals to 0, X equal to 0, and Y equals to 0. Right? That means this surface is continuous across this sort of center region of the coordinate system, right? Because if we have a hyperboloid of two sheets, we would not be able to get any 2D traces at, let's say, Z equals to 0 or X equals to 0, Y equals to 0, right? Because the shape just simply does not exist right here. So that is the key differentiator between the hyperboloid of one sheet and two sheets. So therefore, the problem that we are looking at is we are dealing with it's a hyperboloid of one sheet. Okay, so therefore the correct answer for this problem is delta D.